Okay, morning everybody. So today we have the last lecture of this short tutorial. And basically we are going to talk about the multi-fidelity and multi-objective Bayesian optimization. So the first question becomes, why would we need this type of methods? So remember that in the first lecture, I've illustrated that generally we need optimization methods to be a part of the laboratory operation. So if we run the experimental lab, can be the growth of hybrid perovskites, it can be PLD, it can be pretty much anything. We always have to deal with the multiple optimization and feedback steps. So simple example can be when we use the library of the microcrystals and as a way and use the feedback from studies of this library as a feedback to choose the composition for film growth or to a selection of which composition of single crystal to grow. So we can use the data coming from microscopy in order to understand the processing and select the right film to make, or even navigate in the space of the reagents. So classically, all this experiment planning is done by humans with the relatively small influence of the machine learning. So we know that machine learning can help us. Practically, it is relatively straightforward to use machine learning in order to run the automated experiment when we have a linear workflow, meaning that we have some optimization task and we need to issue the commands that allow us to perform it. It turns out that in many cases, we can achieve the results that we want by bringing the human in the loop. So we have a choice between using the reinforcement learning type methods, which are fully autonomous but require a tremendous amount of data, and we simply don't have access to this type of data in experimental scenarios, or we can bring the human in the loop, and then human basically changes the exploration targets or physics targets or policies during the automated experiment. So for linear workflow, it looks like that we have a workable strategy that can be that was tested for microscopy and generally can be implemented. But the problem is that in many cases we have more than one selection of the workflow. So we typically have multiple decisions that we can make during the experiment, and all these decisions open the opportunities for a different decision space. So, for example, we can choose to make a sample and then go study it on the microscope, or we can decide to make a sample and, for example, we don't like it when we do another sample. Or we may decide at some point to go and collaborate with the theorists. So linear workflows that I've shown, even with the human in the loop, are not going to help us for this type of problems. So we need to think about some other ways to structure the workflows going forward. So the point is that the real world is more complex. And when we look at the complexity of the real world, there are kind of multiple aspects for that. So you sort of have the forks in the road. And today we are going to briefly talk about the two relatively new directions that Bayesian optimization allows us to do. One is the multi-objective optimization, and another is the multi-fidelity measurements. So multi-objective optimization basically is used in the cases when we imagine that we test a battery. So if we test a battery, there are several parameters of the battery that we care about. For example, stability or fading, how many charge-discharge cycles can undergo, cost, manufacturability, power density, energy density. So generally, we know that for each application, we need a different combination of these parameters. For example, if we make a battery for electric vehicle or for the cell phone, we really want it to be stable. But for the cell phone cost really does matter that much. So if the battery costs $20 or $40, this is still a small fraction of the cost of the cell phone. For the electric vehicle situation is totally different, because in Tesla, the battery can be a good fraction of the cost of the whole vehicle. When we talk about the grid storage, the situation is again different, because in this case, cost is paramount. But for example, energy density is not so much. So we need it to be safe, but we can afford to have a much lower energy density than for the car. And the interesting problem becomes, how do we optimize in the scenarios that when we want to balance different factors and we don't know in advance what combinations of the factors do we need? So can we optimize in these situations at all? And the answer is yes, because, and we can prove it by the opposite. So imagine that you make a battery out of something unusual, for example, out of uranium. So in this case, this battery will be kind of dangerous and expensive. So clearly, under no conditions, we would be able to use it. But for other applications, we need to balance them somehow. So the second part is when we are going to talk about the multi-fidelity, refers to the cases when we have multiple sources of data, and we need to make decisions considering the costs, latencies, and beliefs. So altogether, this is very complicated. So to the best of my knowledge, there are no solutions out there that can actually do all of this at the same time. But in principle, there are ways how we can formalize the relative importances of theory, experiment, more complex theory, and make a decision what to do next. So we're just starting to scratch the surface of this decision making, but let me show you how it can be done. So as an important point of advertisement, so the work that I'm going to show has been largely done by Arpan Biswas, who has been a postdoc first working with me at CNMS and then collaborating for the last year and a half. So Arpan is currently on the looking for the permanent positions. So there is a great person out there who actually built the framework that I'm going to talk about. And sort of Arpan's expertise is basically experimental optimization, machine learning, statistical analysis, and putting it all together into the design and operation of the autonomous systems and workflows. So as you will see, kind of very necessary expertise. So the first question is, how do we even do optimization in the cases when there are multiple functions that we want to optimize? So in this case, the simplest way to do that is simply define some cost function, some objective function, which combines, provides some combination of individual characteristics. For example, if we want to make a battery, we can say that the cost plus 3 times the weight can be minimal. So in this case, we kind of try to minimize some linear combination of the parameters of interest that we have, and we define this combination in advance. But then somebody can say that, look, the market is going to change, so the weight of the battery will remain the same. But for example, the cost is going to become twice lower. So what's then? So it turns out that in the case of this multi-objective optimization, what we need to do is to discover what is called the Pareto front. So it's very easy to illustrate. So imagine that we are making the materials for the, let's say, quantum dot emitters. There are 2 parameters that we care about. One is stability, another is intensity. So as you can see, imagine that these dots are the real-world examples of the measurements. So you can see that for this one, there is the sample which has higher stability and a higher intensity at the same time. So clearly, this is not a very good sample. But for this, for example, we have the examples of the samples that have high intensity, but if we improve intensity, then we are going to have lower stability. So for these dots, we can improve stability and intensity at the same time. But for the dots that are laying on this Pareto front, we can improve stability at the cost of intensity, or intensity at the cost of stability. So this is called the Pareto optimality, and that's kind of exactly what it means. It's sort of optimal combination between the properties. Notice that for multi-objective optimization, we cannot discover the object with the properties that are a single object with the properties that we seek. But ultimately, what we want to do is to find this Pareto front in our parameter space. So how can you do that? So obviously, if you have all the functions explicitly and you can evaluate them, then that's just let's calculate everywhere. The difficulty becomes if the functions are expensive to evaluate. So in this case, it becomes a Bayesian optimization, but Bayesian optimization where rather than trying to improve one function, we try to improve two functions, and we seek to discover the Pareto front between these two or more functionalities. So this is a very complex area. So if you are familiar with the basic GP and Bayesian optimization, which you are by now, multi-objective is kind of more complex thing to do. There are several strategies to do that, depending on how you construct the Pareto front in the system space. So you can do it based on the posteriori approach when you try to improve based on the expected results. You can do it based on the a priori approach when you basically calculate your Bayesian Gaussian processes for the each space and then try to navigate this expected improvement. So as often happens, there is a really serious theory about it, which is kind of fairly difficult to understand. The good thing is that most of this theory is under the hood. So by now, there are several multi-objective optimization functions that you can choose as the part of the packages and then just run them. And let's see the examples, how that it works. So imagine that you always want to start with the simple scenario. So imagine that you have two functions, f1 and f2. So this is the function f1 in the parameter space. This is the function f2. So you can see that this one is maximized in this part of the parameter space. This one is maximized in this part of the parameter space, but this one is kind of linear, and this one clearly have some form of bowing across the parameter space. And in the real world scenario, this can be anything. For example, this can be a band gap across the solid solutions, and this can be the photoluminescence intensity. I mean, choose any example that you want. So the question in the multi-objective Bayesian optimization is, how do you construct the Pareto front in this case? And this is how you do that. So you can construct it over the design space, meaning the coordinates between kind of define this parameter space for functions f1 and f2. So obviously they share the parameter space, otherwise we cannot do the multi-objective optimization. Or you can illustrate it in the objective space where the coordinates are the maximum value of f1 and f2. So when we do it in the design space, you see how the algorithm basically navigates it. So you see the initial seed points, and then it sort of start to progress and explore the parameter space for the different acquisition functions. And this is the end result. So this is how our algorithm maps the Pareto frontier and basically tells us that this is the line across which we can find the optimal functionality. So obviously the multi-objective optimization community has come up with the more complex functions. So let's say the F1 now adopts the maxima at the edges of the parameter space, and F2 has multiple maxima. So this is obviously the example of building the model where it is easy to get trapped into the false minima. So in this case, the algorithm kind of also works. The end result is, of course, much more interesting because in this case, the Pareto frontier has a considerably more complex shape. And the end result of the analysis in both cases would be something like this. So, for example, for the simple function, our Pareto frontier looks like this. So we can have functionalities here. This is not what we're interested in. So the optimal ratio between the two functions would be laying on this line. For this camelback function, the Pareto frontier looks like this. So notice that we don't have all the points, so there is no point here, but nonetheless, we can kind of follow the Pareto frontier and say that this is the optimal combination of the properties we can get from this particular system. So this being said, would it work for the real world problems? And the answer is yes, even though it is reasonably difficult to make it incorporated. So the few cases which we in the experimental case. So the few cases that we encountered was the so-called the Ferroionic model, when we studied the ferroelectric material between the bottom electrode and the atmosphere, and there is some electrochemical process on top of this ferroelectric. So it turns out that even if we use the numerical approximation, so we use the, so there is no analytical solution, there is a fairly complex numerical schemes. And if we have these numerical schemes, this system can have a very large number of possible behaviors. So depending on the temperature and the partial pressure of the gas, it can be paraelectric. So then it has the free energy profile like this one, and the hysteresis loop like this. It can be in the ferroelectric phase or something similar, which looks like this. It can be in the anti-ferroionic phase, which has the hysteresis loop look like this. So there is a large variability of the possible behaviors. So if we just try to calculate the possible ways the hysteresis loops can look like, you can see that they can change the loop shape quite a lot. So the question is, can we somehow analyze this parameter space and find in which part of the parameter space the loop area is maximal, or the ratio between the polarization and the loop area is maximal? So define several optimization targets. So if we want to do that, then we actually need to kind of combine the physics approach and multi-objective optimization. So the physics approach is building the decision tree that basically allows us to take a loop and find out whether this is something that we're interested in or not. So we can use it for classification of different phase regions. We can use it for kind of separating the paraelectric phase, ferroelectric phase, and the ferroelectric phase. And we can also define the parameters that we may be interested in, for example, the amount of the stored energy and the amount of the energy loss. So we know that there is some correlation between them. So generally, the more material is ferroelectric, the more we can store, and the more is the loss on switching. But they're not 100% correlated. So there is some ratio when the material stores more energy, but loses, relatively speaking, less. So it turns out that this is exactly the case where the multi-objective Bayesian optimization can be used. So the process can be fairly tedious because you need to build the whole workflow, even for the fully theoretical case, when you define parameter space, select target function, select acquisition function, set the parameters of the Bayesian optimization, including the number of iterations and so on. Then you initialize it. So notice that very often we say that initialization is random. It turns out that maybe random is not the best strategy. So there are other ways of doing that. So then we start to evaluate the behavior of the system. So we perform the calculation, create our hysteresis loop, develop the send it through this decision tree, evaluate our function, and then we sort of send it through the Bayesian optimization workflow. And again, it takes quite a while because you need to train the surrogate model. get the posterior prediction, and then use the search strategy in order to find out how we can build the Pareto frontier. So 2 years ago, that was a big task. It is still a big task, but doing it third time or fourth time is much easier than doing it first or second time. And then the results look pretty nice. So we can calculate. So this is the case where we actually cannot calculate the ground truth values because the calculations will take forever. So that's expensive model. We can sample our parameter space at the very low densities. So in this case, we just take 100 calculations, which already take quite a while. And then rather than calculating on the grid, we basically tell us our multi-objective Bayesian optimization agent to explore the parameter space for us and find the Pareto frontier. And that's exactly what it is going to do. So basically, in the end of this process, we find what is the best possible compromise between the storage and the loss. And we can also see where this behavior is sitting inside the parameter space of the system. So as you can see, these dots all correspond to the low temperatures, and these dots correspond to the high temperature region. So pretty interesting, and we found what we wanted. So if you want to know more about it, this is the paper that Arpan has written about it, sort of published about 2 years ago. And there is a full notebook that allows you to go through the example of this multi-objective Bayesian optimizations. Now, so this is the multi-objective case. So do you have any questions about it before we go to the multi-fidelity? Okay. So let's talk a little bit about the multi-fidelity problems and where do they come from. So let's assume, so for the time being, all our discussions have been dedicated to the scenarios when we have a single expensive model and we want to navigate the parameter space corresponding to the single expensive model in the most efficient fashion. So we know that random grid searches or grid searches are very often not the best strategy. So the Gaussian process is how you can create the surrogate function, and then you basically use the prediction and uncertainty to explore this parameter space more effectively. We also talked about the examples when we know something about the physics of the system, and then we can use the structured Gaussian process. So in this case, we will co-discover the physical model and explore the parameter space at the same time. So this is not a pure exploration, so we have some optimization target. And we also know that if we focus too much on optimization, then we sacrifice the knowledge. If we invest more in the knowledge generation, meaning minimizing the uncertainty, then we need to sacrifice the optimization target, at least initially. And we talked about the deep kernel learning, which essentially allows us to expand the Bayesian optimization to very high dimensional spaces. So we optimize in the space of the possible image patches rather than in the simple parameter space. And the trick there is that we build the latent representations for these complex features dynamically, and effectively we optimize in this dynamic latent space. But in many experimental scenarios, we have kind of much more nuanced situation. So for example, we can have the expensive model that we want to evaluate, but we also have a cheaper model, which is less accurate, but is much easier to measure. So a simplest example of this scenario would be something like hybrid perovskites that I have shown. So in this case, the combinatorial library of the hybrid perovskite compositions is a cheap but less accurate proxy. So it has some functionality of the bulk crystal, but ultimately we are not interested in making the combi library per se. We're interested in using it to guide the selection of the bulk composition. The same type of thing can apply for theoretical modeling. So imagine that you want to explore the phase diagram for some Hamiltonian. So you have to obviously have an option to calculate it on a small grid, like Ising model with a small number of spins. But if you do that, you know that there are finite size effects. So Ising model with it, which is 20 by 20, is not expected to give the bulk behavior. So you really want to use 100 by 100 or 1000 by 1000. But at the same time, you can expect that the smaller model, which is faster to evaluate, will actually contain the significant aspects of the physics of the system. So the question becomes, can you somehow combine the cheap model and the expensive model and use the cheaper model to navigate the parameter space of the expensive model without evaluating it each time? So that's exactly what the multi-fidelity Bayesian optimization is doing. So other examples that are kind of relevant to my own research, and actually the reason why we started to get into this field overall, is the exploration of the combinatorial libraries using the electron microscopy. So combinatorial library is relatively easy to grow. However, electron microscopy is a very expensive method, and using this combi library in order to pick the samples for BioFIB and then doing electron microscopy is kind of 2 weeks of work per each location. At the same time, I can take exactly the same combinatorial library, bring it to the lab with the AFM, and use the AFM to take the images of surface topography or the surface piezo response signal. And you can see that our piezo response signals change systematically going from one end of the combinatorial library to another end. So on the one end, which is ferroelectric, I have beautiful domain patterns, as I should. In the center, I start to have the kind of weird branching domain patterns. That's where the morphotropic phase transition is going on. And on the other end, I have essentially non-ferroelectric material. Or I can use the AFM to do the hysteresis loop measurements and also see that the hysteresis loops change. And then a very interesting question becomes whether I can use the results of the fast measurements like AFM topography or piezo response signal or hysteresis loop measurements in order to help me select locations for the electron microscopy measurements. So obviously, in order to do that, I need to postulate that there is some relationship between the signals that I measure with the atomic force microscope and the observations that I'm doing in the electron microscope. In this case, I know that this is the case because ultimately the AFM measures something related to polarization. And we have domain if there is a polarization. We don't have domain if there is no polarization. So for the hysteresis loops, the relationship is more complicated because hysteresis loops can form because of the several mechanisms. Some of them are related to polarizations. Some of them are not related to polarization. So there is a relationship, but I'm just not sure how strong this connection is. And electron microscopy obviously visualize the atomic positions, and from that I can evaluate the polarization distributions. So both of them are underpinned by the same mechanism, but the connection between them is actually not obvious. However, that's exactly the scenario where the multi-fidelity Bayesian optimization is going to be used. We need to have a strategy that allows us to do a lot of measurements here, and from time to time do measurements using the expensive method. There are, of course, multiple other ways how we can use it. So ARPAN is working on the example of the development of the multi-objective optimization for scanning probe microscopy. So it's exactly the same type of scanning probe that measures the polarization, but his low fidelity model is the basically numerical computation. So if we had the analytical function in this case, we would have used the structured Gaussian process or hypothesis learning. But if we have a model which is sufficiently complex, we cannot use it as a part of the structured Gaussian process model. It is still expensive. We cannot calculate the posterior distributions easily, but we can use it as a multi-fidelity model. So then on the ground level, we have the Gaussian process. On the one level of fidelity, we have a numerical model, which is cheap, relatively cheap, but still requires calculation. And then the most expensive part of the process is the experiment. So of course we can have multiple fidelity cycles. So for example, currently we are working on the proposal for Army, where we say that, look, if we have a combinatorial library of the materials for the fuel cell, we essentially can define three fidelity levels. So the low fidelity level is the use of scanning probe microscopy to probe something related to the electrochemical activity. So the slower fidelity measurement or medium fidelity measurement is measurement of the relaxation time distributions on the combinatorial library. So we expect it to be a more reliable electrochemical functionality, but the high fidelity measurement is making the sample of the composition and making essentially a fuel cell out of it. So this is our target functionality. Making ceramics and making fuel cell and measuring the fuel cell performance takes time and effort, so that's expensive measurement. This is a very fast measurement, but we're not sure what is how it is related exactly to the electrochemical functionality. And this is the proxy where we expect the measurements are the right ones, but we also expect that there is a difference between the combinatorial library and the ceramics. So in our first fidelity cycle is predicated on the relationship between the same sample but two different techniques. Our second fidelity cycle is the same measurement techniques but different forms of the same sample. And obviously you can envision that this type of approach can be applied to any other system. So it can apply to this microcrystal libraries, it can be applied to the spread libraries of metals. And the experiments you can think about can be scanning probe microscopy, nano-indentation, making the bulk material and testing it in the facility, or even building the ready product. And in fact, most of the R&D work and most of the cases when we do something in the lab and scale it to industry is actually the examples of the multiple fidelity cycles from toy models and materials all the way to the manufacturing. So how is it realized? So practically, of course, multi-fidelity Gaussian processes are complicated. So this is the case where it is important to understand the basic philosophy of it and work with the code implementation and then basically apply to your own problem. So this is probably not the case when you want to go deeply under the hood. But the basic principle is fairly straightforward. So we have one function which is defined in our low fidelity space. So this is a low fidelity measurement. We have another function which is a surrogate model in the high fidelity space, so high fidelity measurement. And we have some relationship between the high fidelity measurement and low fidelity measurement. So this is done using so-called fidelity kernel. How the fidelity kernel is introduced is a little bit open issue. So in the code implementation that I'm going to show, the fidelity kernel is simply defined by two parameters, and then we have some constant that, so these parameters are defined in advance, and this constant makes it tunable. So in our case, it is a parameter delta, if which is learned during the experiment. So if delta is small, then you assume that that means that our high fidelity and low fidelity measurements give us the same answer. If delta is large, it means that the low fidelity measurements give us relatively weak information about the high fidelity measurements. So it's in some sense, it's a degree of trust and this is a degree of trust that is learned during the experiment. So generally, this is the example of how it works. Imagine that the red curve is the ground truth. So this is the function that we want to discover. It is available through the high fidelity measurements, but high fidelity measurements are expensive. We want to make smaller amount of these measurements. This is the low fidelity approximation, meaning that this is something that kind of reminds us of the ground truth, but it is something that is much easier to measure. And this is the typical output of the multi-fidelity process. So what we get is, I mean, of course, we keep the ground truth because we want to compare. We keep the low fidelity approximation because this is another thing that we look at. And generally in the notebook, you will see two examples of dots. So the black dots and yellow dots. So the black dots are the examples where the algorithm have performed the measurement on the low fidelity model. And the yellow dots are the examples when the algorithm decided that now it's time to take the measurement on the high fidelity model. So that's basically what we try to do. And in the end, we, of course, evaluate the high fidelity mean function and low fidelity mean function. And of course, each function comes with its own uncertainty. So again, we have two functions, exact and approximate. We build the surrogate models for both of them, and we also try to build the relationship between the low fidelity and high fidelity models, and that is done through the correlation. So this is probably quite a lot to unpack, and kind of that would be absolutely true. It kind of should be this way, but that's the idea. Now, the big and very complex question, which is actually starting to get into the area which is truly interesting, is how are we going to build the acquisition function? Because ultimately, when we talk about the multi-fidelity measurements, we need to define when are we going to measure the cheap function or when are we going to measure the expensive function. If cheap function and expensive function cost the same amount of money or time or whatever, we of course going to measure the expensive function because that's what we want to discover. If, however, the cheap function is cheaper, then we need to somehow balance, make a decision making when we do expensive measurement, when we do the cheap measurement. So as you remember, the choice of the acquisition function, even for classical Bayesian optimization, can be an interesting process. So for multi-fidelity, it's even more so because this is where you need to define the domain expertise. And for example, the recent paper by Xu and Wang basically created the acquisition function, which is a certain combination of the expected improvement. So they basically give the high fidelity expected improvement. They generate the low fidelity expected improvement, which is conditional in this case on the high fidelity one. And then they build the acquisition function, which basically uses the normalized cost ratio to make a decision. So in other words, you take the information gain, expected information gain, how much do you expect to learn from the experiment, and you divide it by the cost of the experiment. So if you expect to learn more from the high fidelity measurement, but then you divide it by cost and then acquisition function becomes smaller than for low fidelity, then you do low fidelity measurement. If not, then you do the high fidelity measurement. And so we are going to go through it in the notebook, but these are just few examples of this exploration for the high fidelity and multi-fidelity GP. So first iteration, 10th iteration, and you will basically see the examples of the two cost functions. One cost function for the low fidelity acquisition, the blue one. Another is the cost adjusted high fidelity. So if the acquisition function for the cost adjusted high fidelity is higher, that means that you take the measurement of the high fidelity function, so do expensive measurement. If the low fidelity acquisition function is higher, then you do the low fidelity acquisition. So this may be a little bit reminiscent of how the hypothesis learning works, but hypothesis learning basically gives the reward. In this case, you calculate the acquisition function and adjust it by the cost. And then if you keep running the experiments, you will see how you basically discover the high and low fidelity functions independently and sort of follow the decision-making process. Now, as I mentioned, there are several applications that we are currently working on, so dependent on essentially illustrations of the method. So one way is to use the low fidelity function as the Ising model, which is very small, and use this low fidelity measurement to inform the selection point for the high fidelity large Ising model. So this is kind of purely theoretical effort. Another project is the hybrid perovskites, where low fidelity is the combinatorial library, high fidelity is the making of the film. The third direction is something that we are doing with Phil Rag group on the Combi libraries and the Chirata for the oxides, where low fidelity is the combinatorial library, high fidelity is the PLD synthesis of the pure compound. But the reason why we're having this tutorial is exactly so that you are aware that these capabilities and this code base exists, and we can think about other examples and other projects where this capability can be useful. Now, one thing that where things become kind of really interesting and go to the places where, to the best of my knowledge, no one from the experimental domains have been before, is the combination of the multi-fidelity measurements and the structured Gaussian processes. So here we know that for many of these scenarios, like Ising model, hybrid perovskite, even synthesis, we have some knowledge about the physics of the system. And I've shown you the example of the structured Gaussian processes, where we basically incorporate the physics as the probabilistic mean function that is learned as the part of the experiment. So it turns out that the multi-fidelity Gaussian processes can also be made structured. And this is, to my knowledge, is the absolutely unique development, at least for the time being. So that was quite a few months of Arpan's work to develop this and build on top of the Maxim's GPACs. But the main idea here is that we still have the multi-fidelity process. We have the fidelity kernel that develops the relationship between the low fidelity and high fidelity function. And we try to learn this parameter delta as the part of the experiment. But now we also have the mean function, which essentially builds the probabilistic model of the physics of the system. So, you can see the example of the low fidelity function and the high fidelity and the ground truth behavior here. So notice that the ground truth behavior, what we want to discover, has a jump. Low fidelity function does not have a jump, so it contains the information about these waves and general location of the maximum, but not its exact shape. And at the same time, we can have the mean function that actually has a jump. So in this way, we combine the knowledge from two different sources of information. One is essentially the data. We can kind of sample our system and they get the data representation. And another is physics. So one tells us that there are variations, another tells us that there is a sharp jump. And this is how it looks like. So if we run the classical multi-fidelity Bayesian optimization, you can see that it's kind of not working all that well, because it tries to balance the measurements on the low fidelity function and high fidelity function. So the yellow ones are high fidelity, black ones are low fidelity. And you see it essentially At some point, it will find the maxima. So you can see that it took a lot of measurements here, and nonetheless, it cannot do particularly well. And by now, you can identify why it is the case. So you see that these uncertainty intervals, they kind of look almost flat. So that means that our correlation length in our kernel is actually very short. And we by now know why it happened. It happened because our kernel tries to discover this jump in the function. And of course, jump means that the kernel has to be small. The price for small kernel is that we are actually not exploring the big part of the parameter space. The benefit of the multi-fidelity measurements is that now we have some belief that these parts of the parameter space are not interesting. And this is the same type of process with the structured multi-fidelity model. So you can see that in this case, the dynamic is more complicated, but basically we discover the jump precisely as we expected to. So that's kind of exactly what a structured model allows us to do. And this is kind of the comparison in the end. So compare the exploration pathway in this case and in this case. So in this case, we basically found something close to the right answer by the price of all measurements being done here. And in the other case, we explored our multi-fidelity, low fidelity function to make sure that there is nothing interesting. And then we used the knowledge of physics to discover the true maximum pretty well. So in this case, we actually didn't find it. So we are somewhere here, and the true maximum is here. So the difference between the blue curve and the red curve. In this case, we kind of got it precisely. Now, is it the whole story? And the answer is no, because once you start to work with the multi-fidelity scenarios, you instantly start to have this concept of belief. So notice that in the multi-fidelity scenario, we have one element of belief, which is our multi-fidelity kernel, which basically tells us what are the correlation between the low fidelity and high fidelity measurements. The problem is that in science, the structure of belief is usually much more complicated. So for example, if I have the theoretical model and the experiment, I don't take the prediction of the theory for the experiment as something which is just a correlation coefficient. I generally say that there are some aspects of theory I believe in, and there are some aspects of the theory that I don't particularly believe in. And there are some aspects of experiment that I believe in, and some aspects of the experimental results that I trust later. So in other words, we put the certain level of beliefs on the both sides, and when we do science, we try to balance them somehow. This is not a part of the Bayesian optimization, even multi-fidelity one. So in this case, you assume that the relationship between your low and high fidelity is essentially defined by one parameter that you can learn. So since, to my knowledge, there have been no past development of the structured Gaussian processes in the multi-fidelity settings, this terminology and this kind of workflows just need to be determined. So there are also other tasks, other types of Gaussian processes, which are sort of similar to the multi-fidelity. So I'll show you the notebook for the multitask Gaussian process. So it's very similar, but slightly different in terms of settings. So in this case, we have multiple observables in the different spaces. Like we can look at same object in the different imaging modalities. We believe that there is a common latent model that emits these observations. And we essentially try to solve the multi-fidelity problem. So we try to find minima in the expansive space suggested by the cheaper function. But this is a little bit different in terms of the physical setting. It may be not different in terms of the practical implementation. So let's look kind of back at the typical examples of the experimental problem that we have in the real world situations, even for the combinatorial libraries. and see what type of the experimental scenarios are covered by the multi-fidelity measurements and which ones are not. So let's assume that we have the combinatorial library, like the one here, but it can be any dimensionality. Let's assume that there are some latent physical parameters that define the behavior of the material as a function of composition. So we know that one of such parameters can be polarization. So that's something we can measure. We know that another parameter can be octahedral tilts, which is also something we can measure. But there can be other parameters, for example, the true concentration, oxygen vacancy concentration, the detailed physics mechanism. So it's a reasonable assumption that there are some latent variables that represent the concentration-dependent physics of the system. We cannot measure them directly. However, we can make some observations which are emitted from this latent parameter space. So whether we measure the electron microscopy, or we measure the topography, or we measure the domain structure, or we measure the hysteresis loops, or we take the micro-Raman measurement, this is the observation that is emitted from the latent space of the system. So the problem, the task for the physics discovery in this case is to have the observational results, run the active learning experiment when we choose where to take measurement, and try to discover what are these latent parameters in the smallest number of steps. So one of the interesting things that I played with recently is to identify the possible scenarios from the experimental viewpoint. So for example, imagine that we have the micro-Raman measurements everywhere. So in this case, we can actually use the simple VIE in order to find latents, but it will not capture the spatial effects, meaning correlations between the adjacent locations. If we have a lot of data, that's not even important. So we can just kind of, if we have a lot of data, we just take it as it is. So another scenario can be active learning when we have one high-dimensional measurement. So if the measured property is scalar, or we have a scalarizer, that's where we use the SGP or hypothesis learning. So if we have the active learning on imaging those spectra, that's interestingly the problem for which we don't have the mathematical tool yet, because in this case we need to emit a high-dimensional observation for the low-dimensional space. So if the space does not have any structure, this would be called the latent variable Gaussian model, which allows us to do that. If there is a spatial correlation that we need to learn, then we need to somehow combine the latent variable Gaussian model with the structured Gaussian process in space. So that's something that still needs to be done. So if we have the scenario when we have full low dimensionality proxy data and active learning for low dimensional data, that's exactly what multi-fidelity GP and SGP does. So here, for example, we can use the something fast like micro-Raman, do the VIE to find the low dimensional proxy, and then use this proxy data in order to enable the active learning by scanning probe or electron microscopy. Or we can use scanning probe microscopy and measure polarization and use this polarization as a proxy to select the locations for the electron microscopy. So other two scenarios are when we have the full high dimensionality proxy data and try to use the active learning from one to another one. So the simplest example is that we have one library where we measure polarization and another library when we use Raman and we want to kind of coordinate the operation of these two tools. So for this one, we also don't have the mathematical framework yet. And kind of co-navigation is when you take these measurements sequentially. So it's kind of active learning version. So as you can see, the number of the tasks that we can encounter even with the combinatorial libraries is fairly large. We have solutions for 2 out of 5. For other 3, we still need to figure out that it can be done and it works. But there is a price for that, because the price is that we essentially learn how to coordinate multiple tools exploring the combinatorial library if these tools measure something that is very different signals. And the final thing that I wanted to mention in the kind of presentation part is that until now, this was all about the correlation. So if we actually co-navigate theory and experiment, then it's totally different problem, because in this case we need to we have expensive theoretical models which gives us the detailed and nuanced answers. We have experiment that gives us detailed and nuanced answers. We need to somehow co-navigate these two locations, balancing the exploration and balancing the fidelities of the theoretical predictions and the fidelities of the experiment. So in other words, there are some parts that we trust for theory. There are some part of the answer we trust to experiment. We basically need to kind of formulate the policies that allow us to establish this trust. It's actually difficult, and again, to my knowledge, this is a new problem. So it appears only in the specific domain scenarios, but maybe not in the general setting of machine learning. So this being said, let's have a look at the at how it all works practically, because that may make it more interesting. So let me share the first of the notebooks. So the notebooks are already on the GitHub, so you're welcome to have a look at them and or just follow my explanations and then look at them later. So this is the example of the notebook that Arpan has developed to illustrate the simple multi-fidelity Bayesian optimization. So let's look at it in a little bit of detail. So we start with the installation of GPUX. So in principle, the simple multi-fidelity Bayesian optimization can be done with the big packages like BotOrch. However, it would be exceptionally, I mean, that code will work on the supercomputers, but it would be fairly long, and you will really have to look under the hood to a very large degree. Also, for the time being, I'm not aware of the BotOrch being used to incorporate the probabilistic model, meaning that you can have multi-fidelity Bayesian optimization, but not the structured one. So then we install everything, including GPUX, including JAX and NumPyra, and then we define our objective functions. So this is the part where the fun starts. So this is our objective function, the one which is expensive to measure. And this is our approximate approximate function. So notice that the difference between the low fidelity and high fidelity function is this term, addition of the linear term and the offset. So it's a relatively simple example. Feel free to explore this notebook in order to modify it and make the examples more complex and more interesting. So one thing that you can do is, for example, choose this function to be a something that has a single peak like a Gaussian, and make the approximate function as something that has a large Gaussian in one location and small Gaussian at the same location as this one, or kind of two Gaussians which are shifted with respect to each other, and so on and so forth. So it's kind of up to you. Then, of course, we define our parameter space, which is just a linear interval from -10 to 10. And then the interesting part here is that we define the fidelities. So these are assigned more or less randomly. So in the beginning, we say that one of the measurement has fidelity 1, another measurement have fidelity 0.95. Don't forget that the correlation between the high fidelity and low fidelity measurements is defined by the kernel, and kernel has the parameter delta that we learn. So in some sense, if this difference is small, we still learn the ratio, the difference in the fidelities in between the two spaces. So it's not fixed. So this is our ground truth. Then, of course, we go through the whole pathway of defining the kernels. So remember from our first lecture 2 months ago, the kernel priors are very important. So they determine how fast the Gaussian process converges, and there is a whole logic to how to select them properly. So if you are purely data scientist, you of course use the half of normal distributions, because why not? If you're experimentalist, that's the part where you make a pause and think, where should this come from? So ideally, they will come from the noise level of the measurement system, expected reproducibility of the experiment. They can be learned. Depending on the experiment, they can be actually determined experimentally at each location. It all depends on how the experiment is configured and what are the relative timings and costs associated with the measurement. So if taking different measurements in the different part of the parameter space takes us the same amount of time as taking measurement at the same type part of the parameter space, in this case, it makes sense to explore points differently. If we have a special case of measurement where measuring 1 point 100 times is as cheap as moving to another location, then our measurement strategy have to be different. So in this case, we need to utilize the local information and get this noise prior from local measurements, just as a reproducibility. So then we define the fidelity kernel. So fidelity kernel, I mean, this is how it's integrated into the full kernel, but the part that you care about is this one. So this is where you take a calculate fidelity difference, which is the delta multiplied by the difference in fidelities, and fidelity kernel is just the exponential function of fidelity minus fidelity difference. So the larger the delta, the weaker is the relationship between the high fidelity and low fidelity measurement. Then everything else is just a RBF kernel, which defines the spatial structure. And then the second difficult part here is the acquisition function. So in this case, you basically calculate the high fidelity acquisition function as the expected improvement. And you define the low fidelity acquisition function. And then you basically have to choose this make this compound acquisition function that balances costs and fidelities. So again, for the first kind of familiarity with this type of approaches, we are going to use the sort of published solution. Realistically, once you define the experimental workflow, this is the part where you pay most attention, and then you look at how much things cost, how long things take to measure, and how much do you trust the measurements to be important. So that's the considerations that go into the acquisition function. So everything else is just visualization. So now let's see how it works. So let's start with the standard Bayesian optimization. So we calculate some seeds, we pick them kind of more or less randomly. This is our ground truth. The crosses are observations. Then we run the usual Bayesian optimization cycle. So by now you have already seen this many times. So this is our ground truth behavior. These are measurement points. This is the high fidelity mean. This is the mean function. These are confidence intervals. So in the beginning, we make a reconstruction. It does look particularly good. Why? Because remember that the standard Gaussian process starts with the assumption that our mean function is 0. And you can see that when we have no points, the function becomes 0. And it also tries to learn the noise. So in this case, it says that, you know what, I don't trust the measurement, even at the locations where the measurements are taken, because I actually think that it should be 0, but there is a noise, and therefore this point is possible. So the green points are sitting on the outer side of the noise envelope. Again, as you remember, if we set the noise prior to be much smaller, then the blue curve would actually go into the green points, because in this case, the algorithm believe in measurements much more. So let's keep doing it. So it keeps selecting the new locations for measurements. So where did it take the measurement this time? So it updated the situation here. Then it keeps learning, and it start to make the noise smaller. So notice that in the beginning, it says that I think that the noise is high. Then actually I believe the measurements more. Then it becomes that, okay, you know what, the noise is actually small. So then you keep doing it, and you see how the classical Bayesian optimization basically explores this parameter space. So let's see if it is going to get to this part of it. And as you can see, it actually never did. So it discovered this minimum and focused on this one. This one, it still doesn't know what goes on. However, now the maximum uncertainty is here, so it is going to explore this part of the parameter space. So after a while, we get our usual picture of the Bayesian optimization on the single function. So you have seen this already many, many times. Now let's do the next step. So now let's do it in the multi-fidelity version. So in this particular case, we have two types of measurements. Again, the cheap, that sample the low fidelity function, and expensive, which are shown by the yellow dots, that sample the high fidelity function. Notice that we start with the 7 low fidelity measurements, 3 high fidelity measurements. So let's run the Bayesian optimization for 15 iterations. See what happens. So now our output becomes slightly more complex, because now we also have the parameter delta, which is essentially the parameter that defines the fidelity kernel. And everything else is the same. So we have the length scale, and noise. In this case, we also plot the acquisition function. So the cost-adjusted high-fidelity acquisition function and low-fidelity acquisition function. So in this case, you can see that the maximum value of the acquisition function corresponds to this location. So correspondingly, we do the measurement here. Once we did the measurement, we update our model, and we update all parameters. We update the delta and the usual kernel parameters. Then we calculate the model again, and again it tells us, you know what, you should take the high fidelity measurement. So we do that again. So with this, we basically found this maximum. So after that, if we calculate the acquisition function, now it tells us that now we have to explore the low fidelity space. So this is what we keep doing. And after that, after we get the full idea about what happens in this maximum, our acquisition functions start to show much more complex structure. So you see that there is a complex structure for the low fidelity function, there is a complex structure for the high fidelity. They kind of sort of go hand in hand, as they should, because in this case, we believe them to be correlated, and they are correlated. And then the process kind of navigates through the exploration of this space, sometimes choosing the high fidelity function, sometimes choosing the low fidelity function to measurement. So once we've done it for 15 iterations, we basically come to the point where, so let's go to the end of the process. So after we've done for the 15 iterations, we sort of have a reasonably good idea that we found the true maximum of this function. So low fidelity data helped us. So, and then we can, of course, follow the training trajectory. So this is where the measurements were taken. We, of course, have the idea about what is our delta, which is how much one measurements inform other measurements, and so on and so forth. So the next example is let's try the same thing with the structured multi-fidelity Bayesian optimization. So in this case, we choose slightly different objective function. So this is the one which is has a jump in it, and the approximate objective is the one which is just a wave. So this is our low fidelity approximation function. This is our high fidelity. This is our ground truth. So basically, we want to use this function in order to help us discover the red function. So the way we proceed about it, again, sort of let's experiment. Let's start with the selecting 10 random samples. So again, these are black crosses are low fidelity measurements, yellow crosses are the high fidelity measurements. So this is what we know before the experiment. Let's see how the multi-fidelity Gaussian process is going to work if we don't have any structure. So this is the example of purely data-driven exploration when there is no physics. So we repeat essentially the same analysis, and in this case, it can be a lot of fun to follow the process. So the notebook is fully functional, so kind of feel free to experiment with it and try it for this function and for whatever function you can come up with, and observe the progression of the acquisition functions and observe the progression of the training process. So this is, it kind of takes quite a while in order to build this mental connection between the multiple curves that you see and the dynamic of the process. So it probably takes to go through the notebook and analysis more than one, but kind of almost keep in mind that we have ground truth, we have low fidelity approximation, which is also ground truth. We have the high fidelity mean function. We have low fidelity mean function, so we discover them at the same time. We have uncertainty intervals for both of them, and we have the observations, which can be low fidelity observations and high fidelity observations. So the things to look at is how when you analyze the progression of the algorithm, you basically look at how close the high fidelity mean is to ground truth, how close is low fidelity mean is to low fidelity ground truth, how the what is the uncertainty intervals for them. So here the trick is that sometimes they can overlap. And you always look at where is the next point for measurement chosen, and whether it is a high fidelity point or low fidelity point. And again, the reason why it is worth doing it is if you're an experimentalist, think about this concept in terms of going to the lab and run the experiment. So it is really worth it to do it in the smallest number of steps possible. So this is the example of the evolution of the exploration space. So we try to find the maximum, and if we do it for quite some time, we would be able to find it, but fairly approximately. So as you can see, this is our ground truth red curve. This is the high fidelity mean. So this is our best approximation of the ground truth. As you can see, it is not particularly good. So it is in most places it is 0. Why it is 0? Because our algorithm have discovered the kernel lengths to be very small. So in the regions when we have high uncertainty, it seems that the function is 0, both high fidelity and low fidelity. The good thing is that we don't particularly care about those regions because we try to find the maximum of the function, and the maximum is here. So what happened is that the low fidelity measurement helped us to find the approximate region where the maximum is, and we took some measurement of this maximum to actually prove that it is here, but we use this low fidelity information in order to basically disregard most of the part of the parameter space. If we had chosen this region, the function to be less greedy, for example, use the exploration rather than expected improvement, or reduce the zeta parameter for the expected improvement, we of course would explore these regions more aggressively. But for the time being, the task was to find the maximum, and this is how the low fidelity function helped us to do that. So let's see how it works with the structured Gaussian process. So again, you've already seen the notebooks for the structured Gaussian process. So we define our model, and we basically create the priors for these models. And then we kind of do the things in exactly the same way. So we create our 10 initial sampling points, which kind of look exactly the same because we use the SID. We define the Bayesian optimization cycle, and then you can see what's the difference between in behavior between the SGP, multi-fidelity SGP, and multi-fidelity Gaussian processing. So in this case, of course, we have the parameter of the function, including a, b, and t. So t is the position of the jump. We have the delta, which tells us the relationship between the low fidelity and high fidelity space. So remember that our low fidelity function does not have this mean function. It's purely data driven. High fidelity actually have the structure. And then we try to learn all of this together. So this is how the process goes on. You can see that our high fidelity mean function has a jump because now we define it. And after a while, we basically define the position of the jump very well. And kind of after we run the optimization for several times, we are actually good to go. So at this point, by the way, we have the structured model both for high and low fidelity. Notice that in this case, we discovered the position for the high fidelity one, but the price for it is actually that the low fidelity also has a jump. And that is kind of makes it interesting because basically in this case, the belief goes in the both directions. So the correlation between the low fidelity and high fidelity function affects the behavior of low fidelity and high fidelity equally. So if the high fidelity function has a jump, then the algorithm thinks that the low fidelity also can have one. Practically, that's can be a limitation, but in order to incorporate it as the part of the active learning process, we basically need to develop the algorithms that allow us to pass some of the beliefs from low fidelity to high fidelity spaces, and those has to be based on the domain expertise. So anyway, this is a kind of further example of how it can operate, and in this case, this is the kind of example of the end result. So now we have discovered the behavior for the case when there is no prior knowledge, and then there is a structured prior knowledge. Okay, so this being said, let's look at another example, which is still running and actually is not on the Colab. How would you run something like this for the real world model? Okay, let me switch to the So this is the example of how something like this will work for the wait a second. The hiding model, yep, and share it. Here we go. So this is the example of how something like this can be used for the theoretical model. So in this case, it is done also in the Colab, which is kind of a little bit of the toy workflow. Practically, of course, it is better to have the Python agent that works on the Colab that communicates to the larger computer which runs the calculations. So in this case, we basically use the toy model, which is a simple Ising model on the square lattice. So very relatively simple case. We set up our 5-fidelity kernel, so the same way as in the previous notebook. And then we kind of evaluate our data for square model. So this is our ground truth measurements. For the small model, we can do the calculations everywhere. And then we basically can experiment with the different forms of the Gaussian processing. So we can try to run the reconstructions, explore it actively. So this is the process of the exploration of the model. This is our observations. We can train it same way as we've done before. So this is the example of the algorithm that basically runs the Gaussian processes and evaluates the model at the same time. So if we go in the beginning, this is where we start. So it has observed this peak with some noisy observations. There are large uncertainties here. So it chooses the next location to run the model. And basically, that's how you explore the parameter space for the Ising model. It's one-dimensional in this particular case, but you can still see that the exploration is fairly effective. So by the end of the process, we get the pretty good analysis of where the maximum of the heat capacity are, and we do so in a relatively small number of measurement points. So we don't calculate on the grid. We only do the measurements at the green locations, and you see that they kind of focus around the maxima. So it's much more effective strategy than just grid calculation. And so this is where we are in the end. For large lattice, the calculations are still running, so I cannot show those. I cannot show this. So anyway, this is it. Therefore, and let me show you another version of the Gaussian processes, which is developed by Maxim, which is the multitask Gaussian process. So superficially, it would be very similar for the multi-fidelity one. The difference is that you don't use the one fidelity of measurement to build the relationship with other fidelity. You assume that there is a common latent process that emits observations of the two type of behaviors, and those are connected through certain correlation metrics. So there are some conditions of how this matrix is defined. So it needs to be symmetric and semi-positive, and therefore it is designed as the kind of sum of some diagonal elements and some outer product of the certain vector W. So the physical meaning of these parameters is fairly complex. So basically, the way that we proceed with it is that we say that we initialize them to be ones or something like this, and then we learn them during the experiment. But this is not anything unusual in machine learning because, for example, when we use the VIEs, we always have two loss functions, the KL loss and the reconstruction loss, and we take the weighting coefficient between those to be fairly random. I mean, we typically take it to be 1. Sometimes we choose it to be something else. So for the practical reasons, think about it as specific hyperparameters that need to be optimized for each specific problem. And of course, one needs to know how to do that, where to do this in the code. But other than that, the structure of this notebook would be exactly the same. So here, Maxim considers the example of the theory experiment matching. The assumption is that the theory is cheap and can be performed over the entire parameter space. the experiment is expensive and can be performed only in some parts of this parameter space. They don't match 100%, but there is a correlation between the theory and calculations and experiment. And again, these correlations are given essentially by the elements of matrix W and the diagonal elements V. So this is the example. So this is theoretical model. Theory is known everywhere. This is the true function for the experiment. This is the locations where the experiment has been taken. So you have access to the blue data, you have access to the black points, but you don't have access to the black curve. So ultimately, you want to discover the behavior of these black curves. So the notebook goes through the examples of, okay, what will happen if you use the normal Gaussian process? So as you can expect it, it's not going to be particularly useful, because if you have measurements here and here, your prediction in between would be fairly unimpressive. So you cannot expect better outcome with the Gaussian process. So with the multi-fidelity multitask GPU, you need to define a number of the latent functions, which is some underlying factors which represent the true physics of the system, which you don't know in their pure form, but you can infer something about them from the observations. So you define the first the kind of behavior with the one latent function. You have a set of parameters. This is actually done for two latents, actually. So you have a set of parameters. You have the length scales. Once you run your experiment, this is what you get. So in this case, we have again the full access to the information in the blue curve, which is great. We have partial experiment, and then we learned two things. We learned the prediction of the experiment. So notice that our multi-fidelity GP prediction is actually remarkably close to the experiment, because it learned how the theory and experiment relate in these regions. It encoded this knowledge in the form of the matrix W and V, and then it used this knowledge to predict the behavior of the theory and experiment here. So if you tell me that the number of these parameters is large and we don't know what they mean, that would be absolutely true. At the same time, it is very clear that this works, and therefore it becomes a question of testing it on the dummy systems that are close to what you have access to experimentally. And then once you tested it, try it in the real world environment. So the same thing can be done in the Bayesian optimization setting, when rather than reconstruct the measurements, we can actually use the theory-guided Bayesian optimization. So we have the theory across the whole parameter space, and then we try to discover the experimental ground truth through the active learning. So rather than trying to reconstruct it everywhere, we actually perform this, the measurement and update our model. So as before, let's start with the simpler model. So this is the blackest true function that we want to discover. So notice that we have measurements only in these two locations. This is our simulation. So simulation is sufficiently close to the experiment, but not exactly. And particularly notice that it roughly points you to where the maximum and minimum are, but relatively speaking, they are shifted. So then we need to define the utility function. So basically our expected improvement. And then let's see how it works. So this is the, where we are. So this is the example of the standard Gaussian processing. So again, by now you have seen this many, many times. We start with the two measurements. Obviously, our reconstructed function is not particularly good. So as can be expected, the maximum uncertainty is on the edge of the interval. So the next measurement is done here. So now we have three measurements. This is our reconstruction. So then we keep doing it for quite some time. So by now, this is very well familiar. we're slowly learning this function, but in the end of the day, what we get is like this. So this is our ground truth. This is our measurement point. You can see that we actually did not find the true minimum. We got trapped in the wrong minimum over here. The true minimum is here. Why did it happen? Because it just happened that none of our measurements taken suggest that there is this minimum over here, and going in the false minimum is kind of very, very common occurrence. Let's try the GPBO. So in this case, let's try the multi-fidelity measurement. So in this case, we have these parameters. So they define how the observations and theory are connected. We have two length scales, so they can be different for the one task and the second task. And see what happens here. So this is kind of where it gets interesting, because even for two measurement points, our predicted function already has the minimum. And this minimum came simply from the fact that the theory suggested that there should be a minimum here. Notice that this minimum is not certain. It's not like we say that, hey, theory predicts that there should be minimum at exactly this value, and therefore this minimum should be here. This comes with a very large uncertainty. And this uncertainty allows us to run the Bayesian optimization effectively. So we calculate our acquisition function. As can be expected, the acquisition function is maximum here. So we have a hybrid exploration-exploitation strategy. So this is our place where we have the maximum of the acquisition function. We take the next measurement. So again, look, we just have three measurements, but we already discovered the general neighborhood where the minimum is. After that, the algorithm will not necessarily try to do the greedy optimization. So we still run the Bayesian optimization, and therefore we dedicate part of our experimental budget in order to explore the places with a large uncertainty. And kind of based on the lecture last week, you can imagine that if this process goes, we can actually change our curiosity of our ML agent, so make it more greedy or less greedy. So in this case, the greediness is constant. We did the measurement here. All of a sudden, our uncertainty dropped. So now we believe this part. We do the next measurement here. So by now, we can reconstruct the overall shape of the function. So the algorithm would want to check this location and this location. So this one, because here there can be a minimum. This one, because here the uncertainty is largest. So overall, iterating several times, you kind of get to the point where after a few iterations, our function is actually very, our function is discovered. And by the end of the process, we are basically exploring only this minimum and try to find out whether it is true minimum or not. So see the progression of the experiment in this case. So this is our true function. This is our simulation that helped us guide the navigation of the space. So we explored several locations to make sure that there is a certain match between the true function and our simulation. Based on this, we formed a belief. So not via algorithm, formed a belief that we actually can trust theory to be approximately correct. And after that, we discovered the true minimum, and then we spend most of our time exploring this true minimum. If you experiment with the values of these parameters that represent the coupling between the theory and simulation, simulation and experiment, you will kind of see that in the beginning we build this trust that helps us navigate. Then actually it will go down because the position of this minimum and this minimum are different. Practically, it suggests that if you run this type of experiments in the real world, at some point you may want to have the human in the loop intervention, and rather than exploring the coupling between the theory and experiment when you're already in the right part of the parameter space, you basically can say, you know what, now is the time when rather than doing Bayesian optimization, I simply switch to the gradient descent or something like this, or go for the fully greedy approach. The reasons for doing that is straightforward, because ultimately you want to do things effectively. You can also say that start to incorporate the physics in the optimization process. For example, you can say that close to the minimum, we expect the function to be parabolic, which basically means that we don't need to spend 20 experimental points in these locations. We can just, whatever, 7 experimental points here.
Sergey, could I interject a question here?
Sure, of course.
So I'm curious. So in this process, would it, as you're starting to evaluate the difference between the simulation and your observation, can you actually use that to feed back to update your simulation or your simulation parameters, and then relaunch this optimization so that you can get a sort of a better match between what you're simulating and what you're really measuring, and to try to get those to converge faster? Is there some way to kind of have that feedback?
Theoretically, yes. Practically, no. So the reason for that is that it depends on what type of simulation model that we have. So imagine that you explore the molecular space of molecules using the density functional theory, right? So in this case, the parameters that are going in the DFT have been determined as the result of agglomeration of knowledge of the very large number of experiments, right? So theoretically, DFT is obviously not first principles, because there are a lot of tunable parameters that they choose in order to achieve the match with the experiment. But you are not going to update the theory in this case based on the one experiment only, because relatively speaking, DFT theory comes with a very high belief, and any single experiment comes with a low belief. If your theoretical model is fairly light and adaptable, then in principle you can do that. So you can use the experiment in order to update the model, and you can use the model to inform the experiment. And there are strategies that do that, so it goes beyond the Bayesian optimization. It's actually a kind of reinforcement learning type of problems. But there is one fundamental problem there, because imagine that your theory and experiment give you a different prediction. You need somehow put belief in the prediction of the theory versus prediction of the experiment. If you absolutely believe the experiment, you are going to tweak the theory until it agrees with the experiment. So this is what we do in the cases of, I don't know, when we use the astronomical data in order to postulate the presence of the dark matter, right? If our observations cannot be explained by the only visible part of the mass of the universe, we postulate that there has to be an invisible mass, because otherwise we cannot explain what goes on, and we believe experiment absolutely. There are scenarios when we actually believe the theory absolutely, or at least we believe it much more than experiment, and therefore we are not going to change it because of the experiment. Simplest example is imagine that we have something, yeah, exactly, JT plus U. Yeah, exactly correct. That's exactly what I was referring to. So, for example, if you have the experiment which suggests that the acceleration, like if you imagine that you have a pendulum and you measure its period. If the period of the pendulum suggests to you that acceleration of the free fall is not 9.8 but is 12, you are not going to say that the gravitation of the Earth changed. You are going to say that maybe there is a magnet under the table, because you trust the theory much more than you trust the experiment, or there is some exogenous factor in the experiment. Same thing applies to the case where you Imagine that you synthesize the material, like was the case with the LK99 recently. You synthesize the material which has the behaviors that can be indicative of the high temperature superconductors. Look how the scientific community responded. Experimentalists started to reproduce the synthesis and speculated that maybe this is a giant diamagnetic behavior. Theory started to calculate the electronic structure and look for signatures of the possible high temperature superconductivity, even though we know that we cannot actually calculate it. However, we know what is there in the band structure that can be a strong indicator of its possibility. Practically, however, in the real world scenarios, we have a much more nuanced beliefs. So we believe that theory can predict some aspects of the material's behavior. Like we usually think that the band gap is kind of okay once you calibrate it for everything. At the same time, the optical band gap can be very different because there can be defects, which basically in experiment, however, we know that there are things that we trust in the experiment, so it's kind of gives us the real information, but there are other things in the experiment which are not very well controlled. For example, we know that if we run experiments in air, there is always a probability that our sample has a lot of hydroxides or whatever. So practically, the way that we balance theory and experiment is much more nuanced than saying that they are correlated. We typically tend to take apart the experimental observations and say that we trust this and this, but not really this. And we tend to take theory and say that this and this is generally right and this one is wrong. So this is kind of understood and we all do that. However, if you want to incorporate this type of beliefs in the active learning scenarios, when you say that I believe this about the experiment and this about the theory, and therefore I choose to plan my next experiment thusly, that has not been done to my knowledge at all, because I mean, folks who wrote the papers and reviews about how you balance theory and experiment intuitively understood it. But this is work of the folks like Paul Anderson or whatever, or Dyson. That was long time ago. So at that time, machine learning simply did not exist at all. So now we have the algorithms that allow us to implement those approaches. But as I said, to my knowledge, it has not been implemented yet, because even structured model or multitask and multi-fidelity models has become available to experimentalists maybe 2-3 years ago. So we are kind of going into the area where not much work has been done, and there was no technical wherewithals to do this work more than 5 years ago.
Right. But I was just trying to understand, the feasibility of this. But for example, here you can envision, based on your observations, if you updated some theoretical simulation parameters and you had a better fit, it may get this to converge faster. But then if you had a separate sample that you come in and repeat this observation, can you establish sort of a correlation or a trust relationship between theory and experiment coming from sort of an agnostic view? I mean, is this a way to kind of help understand how valid is the theory given the experimental parameters that you can, validate?
So in the first approximation, as is done here, we establish the degree of trust. And then we see a very interesting dynamics that in the beginning, trust helps us to explore this parameter space. After that, it becomes a limiting factor, because if we still believe a theory, but experiment points to something different, then we need to start trusting theory less. Practically, from the bigger picture, it tells me two things. If we use something like this in the experimental setting, we need to have the human in the loop intervention when at some point human says, you know what, it's time for me to go greedy. So rather than use the theory as a guidance, I say, you know what, forget about theory. I actually want to focus on the experiment because I need to get the point of the discovery, the real material, which is by parenthetically something that we do quite a lot because a well-known principle from our field is that STM was invented in whatever 80 something, and the theory that explained how STM works was developed 5 years later. So for 5 years, people were building STMs without any theory that explained why is it even possible. So that's not normal. That's not unusual. That's when we actually say that experiment is the true metric of success. So that's one thing. Second conclusion is that multi-fidelity measurements are great. They have the intrinsic approximation of the symmetric link between the kind of parts of the low fidelity and high fidelity measurements. So the trust goes both ways. If I trust you, you trust me. This is not the right way going forward. So if, as a next step, we need to make this trust more nuanced. For example, we trust theory in predict the gross features of the system behavior, but we don't trust theory to predict the final features. So then we need to come up with the considerably more complex algorithms where we formulate these beliefs and we create the mechanism to pass those beliefs. So in Bayesian language, the beliefs are represented as the prior distribution, so we can do that. But you see, the classical Bayesian language doesn't have directionality. So it kind of correlation goes both ways. In this case, we either need to create the policies that pass those beliefs, or we need to make a transition from the correlative model to the causal models. So causal machine learning is the field where the first understandable book with the practical recipes was published about months ago. So it suggests that as physicists, we generally tend to have the right intuition about this type of things, but it would be quite a while before we'll learn how to implement this intuition in the form of actionable codes rather than just following physicists' intuition. That being said, I kind of expect that this next several years are going to be interesting because, as you see, the things that were impossibly difficult 3 years ago by now become something that we can actually learn how to do and do.
Okay, I have another question.
Sure.
When you showed this example, I think this is all really neat stuff, and could be incredibly useful. But one thing is that it seems like you're skipping back and forth between a low fidelity and a high fidelity measurement, and maybe that's not practically what you would do most of the time, because you don't like do a couple measurements on one piece of equipment and then go back and do another measurement on another piece of equipment like TEM to AFM or something. Wouldn't it be more realistic to build a model where you would test a whole bunch of LF and then maybe say, oh, let's go back and test a bunch of high fidelity and then go back and forth in that way?
Yeah, entirely possible. As I said, practically you configure the workflow based on your costs and latencies, right? So we know that time is money, which is true, but we also kind of tend to use slightly different metrics for time and money. And we also know that some experiments simply cannot be done fast. Practically, it depends on what tools you have access to, whether it is easier to do the measurements on them as a single batch. So is it a batch update or not? So there can be even cases when your measurements are asynchronous, meaning that imagine that you have one person sitting on the AFM, another person sitting on the, let's say, Raman or nano-indenter, so they can operate at roughly the same pace and looking at the same combinatorial library. And then the guy who runs AFM follows some experimental strategy based on his results and the input he gets from the guy who runs nano-indenter, and vice versa. So these instruments generate the data at different rates, but you always plan your experiment given your own results and the results of the other guy. So this is an example of the co-orchestration tools. Practically, it can be useful if you have a combinatorial library, and for example, you want to study bifocused X-ray in argon and AFM or micro-Raman somewhere else. So you cannot do focused X-ray everywhere because that takes forever. But at the same time, you want to coordinate the very expensive time of the focused X-ray with the much cheaper time of the AFM or the micro-Raman. But you also cannot run the AFM measurements everywhere because that will take forever. So there are scenarios where which correspond to your case. For example, if I want to use the micro-Raman or AFM as a guide, as a low fidelity measurement to help me select the locations for electron microscopy, then you're absolutely correct. I'm going to do the AFM measurements on the grid because it's going to take me 2 days. But compared to the sample prep time and imaging and image analysis time for electron microscopy, the mapping the whole sample by AFM takes same amount of time as just one electron microscopy measurement. So in this case, I will use this strategy. Whether I will go forward and backward depends on my experimental workflow. So for a single combinatorial library, the one-dimensional one, I probably will do it only one time. But even if my combinatorial library is two-dimensional, so it encodes the tertiary phase diagram, I already cannot run the AFM measurements everywhere. So in this case, I probably will make 100 measurements by AFM, select the location for the electron microscopy, get the electron microscopy data, and choose locations for another 100 measurements by the AFM. So then you will do it in batches. Again, it all depends on cost and the times of the measurement, and you basically configure your experiment based on these considerations, which is exactly the reason why the wherewithals for doing that is not developed for the time being and kind of have to be developed now. The reason is very simple, that people who develop this theory usually have fairly minimal understanding of what happens in the physical and the chemical labs.
Yeah, sure. No, that all makes sense. And yeah, it's pretty hard to have a full understanding of all the theory and all the experiment, especially as we get more and more specialized. But yeah.
But the good thing is that it doesn't require that many people to learn at once, because it's the biggest difference between the machine learning and the kind of scientific community in general, that science is intrinsically competitive. So there is a belief that if I do something first, I publish it, and if you do something first, then I cannot publish it anymore. It's not exactly true, because there are it takes a village, but science is competitive. Machine learning cannot be competitive, because if you start to develop a codes and then you don't share it with anybody else, then everybody gets stuck. So navigating between these two approaches for collaboration and data sharing takes a little bit of effort.
Yeah, I totally agree. And certainly trying to get the right data and the right amount of data is complicated at times. But I have another question, but I don't know if somebody has another one. I could ask a simple little question maybe.
Sure.
It's just in the cases where you're doing the LF, HF, or you're going back and forth between these two kinds of measurements, and then when they disagree, but I guess maybe in the model you're using, they might have relatively low error, both of them, like known error. Then how does the model deal with having a bunch of disagreement?
So as I said, it's very similar to question that Rob asks. So there is a multitask kernel, which basically tells us to which extent one measurement informs the other measurement. So in ARPAN's instantiation, this is just one parameter, which we learn. In Maxim's instantiation, this is a kind of matrix of parameters, but they kind of roughly connected to each other. So in the beginning, we learn to which extent we can trust them, and usually in the examples that I've shown, we can trust them to match the gross features of the system behavior. So in this case, the theory which shows the general trends initially helps us to find the right regions to explore experimentally. After a while, this becomes a problem, because if our trust in the match of the theory and experiment is high, then in the beginning it helps us to find the right regions. And after a while, when we start to zoom in on the true maxima, it actually becomes a problem. So then the model first learns to trust each other, then it kind of learns to trust each other less. Practically, this means that this is a great method, but if we incorporate it into the realistic experimental workflow, we need to always leave an opportunity for the human in the loop and kind of change of our target, because classical implementations of the Bayesian optimization say, hey, these are the hyperparameters. We fix them in the beginning of the experiment, so maybe we tune them, and then we go with these hyperparameters through the whole experimental campaign. This is kind of fine if you deal with the stationary situations, but if the decisions need to be done purely automatically, so if our measurement system is so fast that human cannot respond, of course we go with this approach. However, if our experimental planning is relatively slow, then we kind of would be better off having human in the loop, who kind of monitors the process and sort of tunes the system to be more or less curious. In fact, it's kind of another interesting thing that there is a lot of excitement about the reinforcement learning. So for the last year, already 2 years, kind of minus year at Amazon, I have been working with a group as Google Brain, who actually specializes in the reinforcement learning. And of course, you spend considerable amount of time to learn to understand each other. But generally, the belief that I have now is that for most experimental situations, reinforcement learning is going to be fairly useless. And the reason for that is twofold. First of all, it is very data intensive. And if somebody proposes, let's use it for something, the next question should be, what is your data budget? So you can make Super Mario make things in simulations 10,000 times, but you cannot run the experiment 10,000 times. The second problem with the reinforcement learning is so-called reward hacking, meaning that a reinforcement learning algorithm learns to do things based on the reward that you give it. And the problem is that identification what is going to be the right reward in the experiment is kind of complicated. If you give the wrong reward, the algorithm just kind of goes to the wrong place. Comparatively, Bayesian methods with a human in the loop may be an interesting way to do it right, because they are myopic, meaning that they are planning only one step ahead. But humans presumably are not myopic and can plan more than one step ahead. So then you basically direct the ML agent to do something interesting. And that one has an advantage that you don't have multiple experimental campaigns. You can basically optimize it just for the single one.
No, thank you. That's a good answer. That really helps in the understanding, and I mean, I certainly agree with the human in the loop comment. I think people building these experimental labs generally feel like you're not trying to displace humans, you're trying to enhance humans. So if you want to put it that way.
That's true, but as I said, we are kind of going into the great unknown here, because for the time being, most of the efforts from the automated labs was focused on actually building them and engineering aspects, which is absolutely necessary, because otherwise all these discussions are just pushing hot air. However, and the same thing was for microscopy. So in the beginning, automated microscopy was driven by building the engineering controls to the instruments. As of the last year and or so, the engineering controls become available, but then microscope manufacturers start to have the second problem, that they have APIs that allow people to deploy the codes, and they don't know what this code should be, because the things that they thought are easy, like segmentation, turned out to be very difficult when it runs on the automated microscopes. And generally, there is a complete lack of appreciation of what you're going to do next. So currently, Gerd and I have a collaboration with the Thermo Fisher exactly because we offered them several things that actually make sense. For automated labs, the same issue will appear in the near future because once they're built, the question is what are you going to do with them? So in the beginning, it would be relatively simple, just material optimization, and that's really important. But there is already a feeling in biological community who started this relatively sooner that for the time being, pretty much everything that is done is actually optimization of the human build workflows. So there is a paper from Patrick Riley, who is now VP for Research in Relay Therapeutics, and before that was in Google Accelerated Science, which basically says exactly that. So it's not only my observation. Going a step beyond that would be a very interesting challenge for the next several years, exactly because you need to build into the integrated whole the automation, the theory, the experiment planning, and the update of the theory model. And you cannot do that statically, because if you do it statically, you very quickly come to the point where theory and experiment disagree, and then the question, what's next? So, and that is the scenarios for which we need to plan.
Yeah. That makes a lot of sense, especially for academic labs, as opposed to like pharma or something where they use these labs basically to iterate by 0.001 in some property.
Pharma is different. First of all, pharma has been doing it for 10 years by now, if not more. Secondly, they have a much more rigid workflows, meaning that they have much more formalized processes.
Yeah, absolutely.
And thirdly, all that said, they operate with completely different levels of investment and expectations. But for them, the problem by now is no longer synthesis, it's more testing. If you don't accelerate testing, your discovery of new drug targets would be limited by testing times, not by theory and not by not even by synthesis. So the safe assumption is that out of the 100 of the startups that use machine learning to make new drug targets, predict new drug targets, 95 are going to go out of business when the Series A or Series B runs out. At the same time, the people who now invest into the single cell drug target testing, kind of instead of doing it on the organ or mouse model, do it on the one cell from the mouse. These startups are probably going to be very impactful in the next few years.
Yeah.
Okay, I apologize. I have to move to the next call, but would be delighted to continue by email or kind of one-to-ones. Sounds good?
Thanks a lot.
My pleasure. Bye.
Thanks a lot, Sergey.